Proxima Centauri, the star nearest to our solar system, has long fascinated astronomers and space enthusiasts alike. Discovered in 1915 by Scottish astronomer Robert Innes, this small red dwarf is part of the Alpha Centauri star system, alongside Alpha Centauri A and B despite its relatively close distance of just 4.24 light-years from Earth. Proxima Centauri remains invisible to the naked eye due to its dim brightness. Yet this tiny stellar body plays an outsized role in modern astronomy. The reason? It harbors a planet, Proxima B, that sits in the so-called habitable zone, the region around a star where conditions might allow liquid water to exist. Red dwarfs like Proxima Centauri are very different from stars like our Sun. They are cooler, smaller, and far more long-lasting, capable of burning for trillions of years. Because of their faint luminosity, their habitable zones are situated much closer to the star. In the case of Proxima Centauri, Proxima B orbits at a mere 0.05 astronomical units. Just a fraction of the distance between Earth and our Sun. This close orbit places Proxima B in a potentially life-supporting zone but also exposes it to extreme stellar activity. The planet experiences intense solar flares and elevated levels of radiation, creating a hostile environment and raising questions about its ability to support life as we know it. The discovery of Proxima B in 2016 marked a major milestone in the ongoing search for Earth-like exoplanets. Using the radial velocity method, astronomers were able to detect tiny wobbles in Proxima Centauri's motion, imperceptible shifts caused by the gravitational tug of an orbiting planet. From these subtle changes, scientists calculated both the mass of Proxima B and the length of its orbit. The findings were confirmed by the European Southern Observatory, making headlines across the globe and bringing us one step closer to answering the age-old question: are we alone in the universe? However, observing Proxima B is no simple task. Ground-based telescopes provide only indirect evidence due to limitations like atmospheric distortion and light pollution. As a result, most of what we know about Proxima B, its mass, its distance from its host star, and its potential habitability, comes from indirect measurements. The surface, atmosphere, and finer details remain hidden, beyond the reach of conventional instruments. This is where the James Webb Space Telescope, JWST, steps in. A revolutionary observatory built to peer into the deepest and faintest regions of space. Positioned about 1.5 million kilometers away from Earth at a location known as the second Lagrange point, L2, JWST is uniquely designed to operate far from the noise of Earth's heat and light. Unlike its predecessor Hubble, which orbits our planet and primarily captures visible and ultraviolet light, JWST specializes in infrared observations. This gives it the remarkable ability to cut through cosmic dust and detect light that has been redshifted across billions of years of expansion. JWST's technological advancements are game-changing. Its 6.5-meter wide primary mirror, more than twice the size of Hubble's, consists of 18 hexagonal, gold-coated segments, enabling it to gather vastly more light and see fainter objects. Its powerful instruments include the near-infrared camera, NIR-CAM, mid-infrared instrument, MIRI, and the near-infrared spectrograph, NIR-SPEC. All are designed to work at extremely low temperatures, protected by a multi-layer sunshield that keeps the telescope cool enough to detect the faintest infrared signals in the universe. JWST isn't just a telescope, it's a time machine in a lab orbiting in the dark. It can look back to the earliest galaxies formed after the Big Bang, analyze the composition of exoplanet atmospheres, and help decode the forces that govern stellar evolution and galaxy formation. In the case of Proxima B, JWST might one day provide direct observations of its atmosphere, if it still has one, and even hint at the chemical signatures of life. Why does Proxima B matter so much? Simply put, it offers our best chance at studying a potentially habitable planet beyond our solar system. With a mass about 1.17 times that of Earth, Proxima B is most likely a rocky world, perhaps even possessing geological features similar to our own. Its proximity, just over 4 light-years away, makes it an accessible target for future interstellar probes and an important subject in the study of planetary habitability. But it's no Earth twin. One of the most significant differences is that Proxima B is likely tidally locked meaning one side of the planet always faces its star while the other remains in perpetual darkness. This creates extreme temperature contrasts between the blistering day side and the frigid night side. However, there's a narrow zone between the two, a twilight region known as the terminator zone where temperatures might be moderate enough to allow liquid water to exist. This ring around the planet could serve as a potential cradle for life, harboring conditions that are neither too hot nor too cold. Despite its promising traits, Proxima B faces enormous environmental challenges. Proxima Centauri is known for violent stellar flares, massive outbursts of X-rays and ultraviolet radiation that could strip away any atmosphere and bombard the surface with deadly radiation. For life to survive, Proxima B would need a robust magnetic field to shield itself from this cosmic onslaught. Without such protection, its surface might be barren and sterile. Yet even here, hope remains. Life, if it exists, could adapt to the extremes, possibly thriving underground or beneath ice layers, protected from radiation. At *Waves Discovery*, we believe that the search for life beyond Earth isn't just a scientific endeavor. It's a journey of human curiosity, creativity, and courage. Proxima B represents a beacon on that journey, a distant yet reachable world that invites us to question what it means to be alive in the universe. What if everything we know, every particle, every force, every law of nature, was merely a vibration of a cosmic strain in a hidden realm of dimensions? What if wormholes weren't just science fiction portals, but actual tunnels through the fabric of reality, folded into the very geometry of the universe? These aren't just speculative fantasies. They are part of one of science's most ambitious undertakings, the search for a theory of everything. Let's begin with a familiar cornerstone: Einstein's general relativity, a framework that revolutionized our understanding of gravity and spacetime. According to Einstein, massive objects like stars and black holes distort the fabric of spacetime, creating curves that we perceive as gravity. Yet even this elegant theory imposes limits. For instance, it forbids anything from traveling faster than light, a rule that directly challenges the feasibility of stable wormholes or shortcuts through space. In science fiction, wormholes are cosmic gateways to distant galaxies or parallel dimensions. In reality, Einstein's own equations allow for such phenomena, but under extremely exotic conditions, ones that may not exist in our observable universe. Still, the idea of wormholes endures, not just as a mathematical curiosity, but as a symbol of human wonder, a whisper from the unknown inviting us to reach beyond. And it is from that same whisper that the pursuit of a deeper, all-encompassing theory emerged. Enter superstring theory *, a groundbreaking idea in theoretical physics that attempts to bridge the chasm between Einstein's gravity and the strange rules of quantum mechanics. Spearheaded by brilliant minds such as physicist Moku*, this theory proposes that the universe is not made up of point-like particles, but of incredibly tiny, vibrating strings. Just as a violin string plays different notes depending on how it vibrates, these cosmic strings resonate at different frequencies to produce the particles and forces that govern our world: electrons, quarks, photons, and even gravity. Within this framework, the universe transforms into a symphony of vibrations, with every element of existence arising from a fundamental melody written in the language of strings. But for the orchestra to play in tune, superstring theory demands something extraordinary: extra dimension. Not just the 3 of space and 1 of time that we experience, but up to 10 or 11 dimensions curled up in such tight configurations that they remain unseen. Think of a sheet of paper rolled into a scroll. From far away, it appears two-dimensional. But up close, you realize it has depth and curvature. Similarly, these extra dimensions may be all around us, shaping gravity, dark energy, and the fundamental constants of nature, yet hidden beyond our perception. Though bizarre, these hidden realms could hold the answers to mysteries ranging from the behavior of black holes to the accelerating expansion of the universe. Superstring theory isn't just physics, it's also deeply mathematical. Its equations have sparked a renaissance in mathematics, forging unexpected links between abstract math and physical reality. It's a fusion of two grand intellectual traditions, mathematics and natural philosophy, uniting in a bold attempt to reveal the architecture of the cosmos. But there's a catch. Despite its elegance and potential, superstring theory remains unproven. No experiment has yet verified its predictions. The tools we need to explore its higher dimensional landscape, colliders powerful enough to probe these tiny scales or telescopes sensitive enough to detect gravitational signatures, do not yet exist. As a result, string theory continues to evolve in the realm of thought and math, standing on the frontier between imagination and empirical science. And yet, recent breakthroughs have brought fresh hope, particularly in the realm of quantum black holes. These enigmatic objects, where gravity is so intense that even light cannot escape, have long posed a major challenge. What happens inside them? Do they destroy information or store it in some strange quantum form? Solving this riddle could unravel the deepest layers of reality. Now, multiple research groups have begun making surprising progress. Instead of tackling the full 10-dimensional framework of traditional string theory, they've focused on simplified 2-dimensional versions. And the results are intriguing. Within these reduced models, string theory seems capable of describing the behavior of quantum black holes with remarkable precision. It's as if we're finally starting to glimpse the rules behind the universe's most secretive corners. One of the key figures in this exploration, Edward Witten of Princeton's Institute for Advanced Study, famously described superstring theory as 21st-century physics that fell into the 20th century by accident. His words still echo today, as we edge closer to a breakthrough that could transform our understanding of time, space, and reality itself. Black holes are more than just cosmic oddities. They are crucibles of knowledge, testing the limits of physics and opening portals into deeper truths. These collisions and emissions paint a complex tapestry of motion, matter, and energy, hidden behind the veil of gravity. But perhaps the most important legacy of these efforts is the mindset they foster. The pursuit of a theory of everything isn't about reaching a final answer. It's about asking better questions, ones that stretch our imagination and challenge the boundaries of what we believe is possible. In that sense, superstring theory and its implications, wormholes, extra dimensions, and quantum black holes, are not just theories. They are invitations to dream boldly. At Waves Discovery, we believe the future of science lies in wonder. The path ahead is uncertain, filled with paradoxes and impossibilities. But it is precisely there, in that space between mystery and knowledge, that the most profound revelations await.